Okay, so start my multiple recording devices here. Excellent. So today and the next time, we're going to talk about something that I think is ignored a lot in statistics, which really bugs me because, frankly, people care so much about doing t-tests and analysis of variance and all these things, these inferential procedures, they forget about the importance of this kind of stuff, which is called exploratory data analysis. You like that transition? Pretty cool, eh? So you don't find anything about a data set. First, you have to understand the data itself. Within themselves, if you think of the word data as a plural, which it actually is, singular is datum, but whatever. If you're writing, say, these data, just please. Because too many people say the data, and it makes me feel old, that I'm going, no, it's these data. Okay, so you gotta understand your stuff first. Basically, what we're trying to do here is to get a feel for our numbers. So you're just basically looking at stuff and doing it. This is done for yourself. This would never be something, or very few of these things would ever show up in an article you're writing. It would never show up in your thesis. They might. But it's just ways of understanding the data before you actually manipulate it in any way. So it's going to be easier to find mistakes that you may have made. You may have made coding errors. Right? A lot of times when you're writing, when you're doing anything that's not automatic, you will have to transcribe numbers into a spreadsheet of some sort, into SPSS, which is basically the interface for the spreadsheet. So you have to write stuff down, and let's say it's numbers 1 to 7 for the old Likert scale. 1 strongly agree, strongly disagree, whatever, and suddenly you see a 77. Well, that's probably because you get the 7 twice. So it's going to be easy to spot that because you just look at a bunch of numbers and go, whoa, that's not possible. It's a really important thing to do because a lot of times people skip this step and that'll screw up an average pretty badly. It's an order of magnitude bigger than 7. What actually happened in the research you got? Like, what are the effects? What's really there? It's going to be easier to figure out what actually happened if you look at the data themselves rather than just look at averages. B.F. Skinner said, the average describes the behavior of no animal. And my PhD advisor, Sarah Shuttleworth, used to say, inferential statistics are there to prove what you already know. You should be able to look at a graph and say, I see what happened in my experiment. It seems to me if you can't do that, you can't just look at a graph and go, I see what happened, you probably don't have anything that's that interesting. It's also easy to find odd values. One of the assignments that I was given when I took a course like this, I TA'd a course like this, and eventually taught a course like this, and when I was a grad student. And we were given a data set of about 500 records, 23 variables, and the idea was, a friend of mine, Todd, a senior graduate student at the time, he had a little project he was doing, was trying to develop a questionnaire that was as accurate as a physiological measurement to see how many cigarettes people smoke per day. Because it's an easy thing to do physiologically. I get a saliva sample from you, and I send it off to a lab, and I see how much nicotine is in your saliva and how much cotinine, which is a stable metabolite of nicotine, and we know the half-life. It's easy to do, except go to a doctor's office, let's say you're trying to quit smoking, go to an MD, and he or she says, spit in this thing. That's a little intrusive. Wouldn't it be easier to say, answer these 3 questions, and I can see how many cigarettes you smoke? This is what Todd was trying to develop. So what she did, but the neat thing was, he had all the data, so he would just give it to us and say, figure out what happened. And by the end of this course, you'd be able to do that, by the way. So build a model that predicts cigarette smoking per day. And then going through the data and finding someone saying they smoked 400 cigarettes a day. That's through the Olympics Go Pro. That's professional smoking. Nobody smokes 400 cigarettes per day. That's a coding error. Or that's a guy answering with a lie because he thinks he's clever. How many? What's 25 in a pack? So you get what? It's 4 for 100. That guy's smoking. Nobody's smoking 16 packs of cigarettes a day. It's probably really 40, isn't it? Right? But we don't know. We don't actually know the answer. So we probably just have to throw out his data. But it's better than keeping his data in, or her data. I think it was a him, though. Right? It also had, when did you start smoking? One of the data was called year start, I think it was called. And people remember pretty well because when you smoke, your first one's the greatest thing you've ever done, and except for the most recent one you smoked, which was also great. But you usually remember, I was this age. And one person had that they were, what was it? Well, it was a single digit number. It's like, it seems unlikely. It's probably not 6, it's probably 16. Right? Yes, I know, we've all seen the baby from Indonesia who smokes on YouTube. It's horrible. And the chimps that smoke. There was a show on years ago called Honey, We're Killing the Kids, which is a bad name for a show. And it was about people having bad nutrition for their children. It was on the Food Network. I don't know why. It used to be a show that was about cooking. No, now it's just stupid stuff. Oh, look, Cupcake Wars is on. But they interviewed this woman and her kid who's like 10, and he's like morbidly obese. And he smokes. He started smoking when he was 4. Do I have to quit smoking too? The kid says. And the intervention person says, you have to quit. It's the strangest thing I've ever seen. Do I have to quit smoking too? And then they showed his bedroom. He's got ashtrays everywhere. His mum thought that was cool. So it's not a problem, really. It's a British show. I was just doing that accent for no reason. It's weird. See, so that case, but then you also have to think, if the guy in the survey actually started at 6, or this kid started at 4, fine. I mean, not fine, but weird, but okay. But are we going to actually accept that as something that we... I don't even accept it societally. I don't think we should. I mean, do we think that they're even in the same population as your average smoker? So maybe we want to, even if it isn't a mistake, we just want to remove their data anyway. And that the only way you're going to find that stuff out is if you look at the numbers themselves, instead of just crunching them into a thing and getting a mean and some standard deviations and going, here you go, graph. Even just looking at the raw data is important. Okay? So, what this is called is exploratory data analysis. There's actually a book by a guy named John Tukey who developed the Tukey test you may have heard of, which is a post-hoc test analysis of variance. He wrote a book called Exploratory Data Analysis, which is a barn burner, a page turner. Movie rights have been sold. It's a big Michael Bay production now. It's going to be a... it's a Brad Pitt vehicle. It's going to be great. He stars as Standard Deviation Man. It's... I don't know. I'm going to stop now because I'm really just entertaining myself, and obviously most of you don't know who the hell I am. But still, so John Tukey writes this book, Exploratory Data Analysis, and it's about things like graphs and means and standard descriptive statistics and stuff. You know how you were told in 2126, and rightfully so, by the way. It's not a criticism of anybody, because I do the same thing. I say, you know, you think your statistics, we're going to talk about that for 20 minutes, and then the rest of the course is how to do t-tests, which is all fine, by the way. The thing is, doing this exploratory data analysis allows you to generate hypotheses and just get a feel for your data, too. You should know what your data look like. You really should have a feel for it. Okay? Any questions so far? Okay? So you're going to get an idea of how your experiment went, and I'm just going to say experiment. Maybe you did a survey, but whatever. I'm going to say experiment. You can do surveys, you can do experiments with surveys. I'm saying it could be correlational, but if you do your honors thesis here, it has to be an experiment. You don't lose any richness in the data. It's all the numbers are still there. Now, it's not just looking at numbers. It's not like the matrix. Numbers, matrix, nothing. Oh, I see, just not funny. You got the reference, just not funny. Tough group this year. Tough crowd. Note to self, tough crowd. So you might not just look at a bunch of numbers, but you might look at a whole bunch of numbers from two different groups. Right? So let's say it's number of words recalled, and we have retention interval. So you get a list of words to remember, say 10 words, and then you got a 5-minute retention interval for one group, and then a 1-day retention interval for another group. So 5 minutes, and you see numbers like sure. So 5 people per group, and this is the one. So we have 9, 8, 6, 7, 10. Doesn't matter what the numbers are. Please don't write them down. And feel free to write. I don't care. Write down whatever you want. I'm saying this isn't important. But that's going to be our 5-minute group, and then our 1-day group. 2, 1, 3, 1, 4. You can tell right away just by looking at those numbers. There's something going on there, and you can even tell if there were, instead of just 5 per group, if there were 50 per group. If they looked like that, if that pattern was consistent, you'd be able to tell something happened. Something happened. Right? You know, and I think you all know what you do here. You do sample t-test, blah, blah, blah. But they would just confirm what you already know. In this case, you know it just by looking at the raw numbers grouped into 2 groups. When I was in graduate school, I would meet with my supervisor once a week, and we would just look at graphs I generated. Or sometimes I just bring me data sheets. And we just look at numbers. Right? And with my honor students, when they start collecting data, I say, just bring some numbers to me. Bring it to me. We're just going to look at them. And usually we can figure out if something went on. Sometimes we make it go a little further, make a graph, whatever. But the first step is this, if you can. If it's doable. It isn't always, but if it's doable. All right. Okay, these don't mean anything. I just have some numbers that I've now put into a table. Aha. So we've got the x's and we got some frequencies. Let's say those are a statistics test and it's at a 35. Okay. That's not an unreasonable set of numbers. How many people in the class are 1, 2, 3, 5, 8, 9, 10, 11, 12? It's a small class. Fair enough. So this sort of relative frequency kind of table has allowed us to look at this and say, what kind of conclusions would you make about this class? It's a stat, let's say it's a stats class, that's at a 35. Would you make any conclusions here? Just by looking at these numbers. Can you? Because I think you can, but what are some interpretations you could make? This is an audience participation part. This is where you talk. You go ahead, just talk.
So if we were to put on a graph the distribution would look relatively normal?
Yeah, relatively normal. I think that's symmetrical, you might say, right? I kind of look at it sideways because I'm like that. Right in the middle there, 25. Most common answer, 25 out of 35 is okay. What's that in percentage? That's 5/7. So that's 71.2, I think. That's good. That's a good grade. We got a B, class level B students. That's what you would expect. B mean good. Look in calendar, B good. A excellent. C satisfactory. Which I guess you guys all know by now. Remember in first year when the first time you got a C and went, what? What? And you went to the prof and said, got a C. And, yeah, I see that. But yeah, C means satisfactory, means it was okay. Oh, I thought that was like B plus. No. read the calendar. My favorite one I used to do this in Newfoundland a lot. This is not meant as criticism of Newfoundland, but it kind of is. No, it really isn't. But it's because colloquially people have it. Newfoundland English is different. And I'd have people come to me and say, "But sir, I know some material." And I'd say, "How do you learn English?" But yeah, you're right. This is good. You're right. It's like a graph. You can think of it that way. And the most common thing is like a B. What other kind of conclusions could we make? Just there's other possibilities. I got a couple I can think of. So what's 50% of 35? That's what? 17 and a half, right? That'd be a pass. Ooh. All but one person passed the test. That's the kind of thing when I see something like that, it makes me happy. Because it means I'm doing my job okay. What else could you conclude? Conceivably conclude. What's possible from this set of numbers? Just talk. Go ahead, anybody. Yeah, go ahead.
10's the outlier.
10's what?
Outlier.
It's an outlier, we can call it an outlier. Somebody did very poorly. Yeah, because that's way bad. Though, let's see, the most common thing is 25, the mean's probably close to 25. That's only 10 away, that's 15 away. Yeah, it might be an outlier. There's really no real definition for outlier. Anybody who tells you there's a definition for an outlier, say, no, there isn't. Because everybody's a different one. But you're right, to me that jumps out. This one jumps out, somebody doesn't get it. Somebody didn't come to class. Or download the podcast or watch the YouTube video. The things I do for you people. Somebody maybe somebody should change majors. I'm not on one test. You never, ever, ever, please, ever, ever, ever make that decision based on one assignment. It's like the guy who once got a 60 on an essay. Well, that's it. I'm changing over to political science. I actually seriously thought about that until a friend of mine pointed out how arithmetic worked to me. What's the student your overall average? Oh, well, that's true. Nothing. Or maybe this person was in the wrong class and was too embarrassed to not leave. You ever do that? Like in first year, you wouldn't do it now. In first year, you didn't know where anything was. Walking around, you go sit down and someone says, "Welcome to third year chemistry." Well, that happened to me. I was in first year, and it was my second day. And I don't see well, so I'm like, look at room numbers like that. Like seriously, right? And so I'm walking around. And I get in this room, and it's full of students, so that's good. Remember, there's 28,000 undergraduates at Western. I was one of them. Walking around, I go sit down. And it's like a fourth year chemical engineering class or something crazy thing. And I was good in chemistry. Like I was really good in chemistry in high school. I got 103 in grade 13 chemistry. With all the bonus points. Can't remember any of it. I could probably balance an equation still. It's probably all I could do. But I was really good in chemistry. But I wasn't taking chemistry at university. And I thought, well, I guess I can't leave now because it's really embarrassing. What I'll do is I'll just sit here for the first hour, and then when they have the smoke break, it's 1984, I'll just leave. So I did that. I sat there, missing the class I'm supposed to be at, by the way. And I thought, oh, this is harder than chemistry in high school. This is really hard chemistry. And I never. But I was embarrassed. So maybe this guy shows up, he's embarrassed, then he writes the test anyway. This is me in first year. So we can make some conclusions. Oh, somebody did really well. Wow, somebody's perfect. That's good. That's the person, when you get that, I usually write on your test, would you like to teach the rest of the course? We have a few people here that are really kicking ass, though. We have 4 people out of 12 that are getting, those are like A+ grades, or high A grades. That's nice. So we can make some nice decisions here. Class is going okay. So that frequency table allows you to do stuff like you can take the sum of the x's, that's the x values, the scores in the test, and multiply it times the frequency of those. You can sum all those together, which I just did there. Oh, there should be a closed bracket. Oh, that 0 should be a closed bracket. I didn't shift, obviously. It's 309. And we're dividing by 12, which gives us, what am I doing? It doesn't matter. We can take all that, divide by 12, and we get the mean. So that's pretty easy to do. We haven't lost any richness in our data, we just organized them at this point. Sorry, I went ahead, it doesn't matter. But look, you can also use this to make, you're saying a graph, you're right, relative frequency histogram. Like that. How did I make that? I typed a bunch of things into a program and it came out. I don't know. And you can tell that I wouldn't put this in a paper. This wouldn't be something I would, not that anyone would ever publish their class grades. That would be weird. That's an easy publication. I guess I did it once, but it was because I was comparing podcasted classes to non-pod, and there's a 6% increase since I started podcasting lectures. Is that right? 6.1? I think it's something like that. It doesn't matter. I would never put this in a thing because look at this ridiculous scale on my y-axis. It's frequency there, numbers of people, 1.25, what is that? But all this, I did this automatically. I used the program because this is Mac stuff, so I didn't use Excel. I used numbers to do this. Same kind of thing, though. I just typed these numbers into a spreadsheet, and I looked up how do you make a histogram, and I did some clicking, and that came up. Right? This is just for me. It gives me an idea of shape, and this is where you're right. Outlier, you might have a point, because that doesn't look like it. One of these things does not belong here. It's very Sesame Street. You still do that on Sesame Street? One of these things when you guys were kids? I watched Sesame Street when it started in 1969. Because I'm old. I remember Mr. Rogers stuff. That's how old I am. I remember the Vietnam War being on TV. And it wasn't just a show, it was the news. Yeah, but that tells us something. It's in fact, the nice thing with this is, in fact, we have again lost no richness in our data. We could actually reconstruct the data set from here. You could literally get a list of all those numbers. It'd be easy to do. So that's useful. This isn't going to be that useful in any sort of presentation, in a paper or anything like that. But at least this has allowed you to do get a feel for yours. Questions so far? Everybody bored? Good. It's all stuff you know. So we can reconstruct that. So it would be trivially easy to do. And it allows you to spot something odd. And again, outlier is a possible word here we could use. Something weird is going on here. Somebody's really in trouble in the course. See, if I saw this whole thing shifted over, and the most common score was 17, which is, remember, 17 and a half is a pass, I would say to myself, that test was too hard, but the distribution looks okay. And this, in fact, wouldn't be a class like this. This class tends to have a negatively skewed distribution. It's bunched up to the right. Because this is what a 21-26 class looks like at the beginning. Normal-ish. And these people all dropped the course. No, seriously. A lot of them did. But eventually, people all move over and it all bunches up at the other end. That's just how stats marks look. I expect them to look that way. But if it was all, say, shifted over, I might say the test is too hard, but the distribution looks okay. So I might, and I hardly have ever done this in my career, I'm like, let's do something about that. I might do something about that. And that something is never make the next test really easy. The something would be to adjust those scores. I hate that when the test is too... You ever had that when the test is too easy the first time? So then the prof decides they're just going to screw you on the next test? Yeah, I hate that. I got a lot of hate, though. I mean, the list of things I hate, it's a long list, man. Questions? You good? Now, you might have categorical got it. You look at a histogram, you get a bar graph. Good name, bar graph. Do a pie chart. I don't know why people do pie charts. I hate them. I think they're big in business. I'm just guessing. I don't know business. I'm just guessing. I'm an accountant. Yeah, boy, you found stacks too exciting? Yeah, pie charts are fun. Remember when we call them infographics. I like calling them charts and graphs. I don't have to invent a new multisyllabic word so I can put a meme across it. Shut up. God, I hate people. I'm really not this negative. I'm just kind of playing a character. Actually, I am that negative. So it's pretty much the same thing. Your x-axis doesn't really have a scale. They're just categories, right? So let's pretend it's a Stack 21-26 class. Let's just pretend. And we got 38 psych majors, 15 sociology majors, because maybe they want to take it, I don't know. 18 CESD majors and 5 biology majors. In fact, this is the actual demographics from the Stats 21-26 class I had. 2007? It's pretty old. Those are real data. It's back when sociology students took our stats. Then they had their own, because ours was not theirs. Still get the odd sociology student in that class, get the odd CSD students, and always the biology students. Now it's almost just psych and biology. But that would be a boring graph. I don't know why I put these in this order. I think it was the order I put them in the spreadsheet I made. But there is no order to this anyway, is there? There really isn't any. So there's no reason to do anything with it. It's more for me to just get a feeling like, oh, plurality of students are psych majors. And as much as we may all think that psychology is better than everything else, because it is, demonstrably so, we can't put it, is psychology, let's say we put psychology first here, because the more, it's like golf, the more close you are to zero, the better it is. And we'd have to put these two over here and bring biology over here, I think. Is psychology 1 better than biology? But 2 better than sociology? What the hell does that even mean? So you can't do that. It'd be like if you had, it's like TV channels, right? You know the channels have numbers, right? And I think on Shaw Cable, I think channel 2 is the weather channel. Because I know when my cable box reboots, it goes back to channel 2. But the channel I watch, let's see. So like 225, let's make the math a little easier. 222, I don't think it is, but I'm going to make math easier, is Sportsnet Ontario. And I want to watch a hockey game. Is Sportsnet Ontario 220, or 111 times the channel? The weather channel, not really. Maybe. So sometimes things even have numbers doesn't make a difference, right? But that's what we're talking about here. This is, again, just to give yourself a feel for stuff. There's a pie chart. It doesn't help me any more than this. Who likes pie charts? I don't care if you like them. I'm just curious. Does anybody like them? Does it help you any more than this? I mean, it's fine if it does. I'm not going to get mad at you. I want to know why people like them. Does anybody like pie charts? You do. You like pie charts. You're pro pie chart?
Oh, yeah.
What do you like about them? Because I don't know. I don't get it.
Because I can see the whole.
Okay. You can see it all. Okay. They're all easy to compare to each other. I like that. That's maybe I'll rethink my view on pie charts. They just don't show up in science things, so I just don't see them that often. I guess that's probably all it is. I'm not used to them. That's a good point. You may have something. I will moderate my views. What's the chance of that happening? Okay. Virtually nil. Okay. Those are qualitative variables. We don't deal with those a lot. We deal with them some. And there's nothing wrong with qualitative variables. Hair color is a qualitative variable. Sex, male or female, is a qualitative variable. Right? And I mean, biological sex, okay? I mean like having a Y chromosome. Okay? So you're not all getting mad at me? I mean like having a Y chromosome or not. Nothing about gender, I'm talking about, okay? So don't have a committee that's going to investigate me. I'm always afraid of committees, and it's never happened to me in my life, but it could start. I'm just saying. Or species. I do comparative stuff. Compare species. Those are. Is it a chickadee or a junco? Those are qualitative things, right? And they're perfectly sensible things to study. Nothing wrong with it. But a lot of times you have quantitative, or group 1, group 2, though it's 5 minutes one day, it's getting pretty quantitative. So quantitative stuff, of course with these, as I said, we could use a histogram. I looked at that and I almost read Instagram, and that's sad. That's really weird. We can see central tendency, which is, you know what that is, like average, right? We can see the spread of something, right? And the shape. So the central tendency, that's average, mean, median, mode, those things. We can see the spread, just how spread out something is. And we can see the shape of something. Of a distribution, of a bunch of scores, of a batch of numbers. Okay? So, skewness. Positive skew, this always really pisses me off. Because I think it's said backwards, even though it's not. I would think that would be positive skew on the left here. And that would be negative skew on the right. But I would be wrong. Do you know how you can remember this? The tail tells the tale. It's not Cheryl Reed Elder taught me that. It's the one thing she's taught me. Just messing around. I'm messing around. We've been friends for 21 years. 20 years. But I remember saying to her, and I get it wrong all the time, and she said, David. Because that's what she called me. Everybody else calls me David. David. The tail tells the tale. Oh, that's good. So I'm giving her credit and making a little fun of her. Which, that's good. It's really, I never forget it now. I never forget it. So like I said, you have a negative skew in a stats class in grades. There's a couple reasons in this class. A couple reasons. Because you've all got through 2126, the intro stats, and because you're taking this because you have to, it's a required course, so you tend to pay attention. And people that want to do the honors degree, they know they have to get 70 in this course, so they pay attention. They try. People are engaged, right? Good enough. So positive skew in a class like that that's often the very beginning of statistics. That's usually more normal, actually. I'm trying to think of something that is a positive skew that, like in grades of a class, I can't. Intro psych looks a lot like that. Intro psych looks a lot like that. It's, assuming this right around here is about 50. People are bunched up, but there are a few people who have just found it really easy. Right? Few people find the course really easy. Most people get B's and C's in that class. And then there are people who literally just abysmally fail. But that's because it's a first-year course. And a lot of people in first year shouldn't be here, right? You know that. You've met many of these people. You went to school with them 2 years ago. Right? Because they'd say, I don't know how you keep up with the reading. And you're like, you read the book. It's not that bad. You don't even really have to. Read the important bits. I'm not suggesting don't read books. I'm suggesting there are strategies to how to study, right? Or the people that just showed up because they could get away from their mom and dad and they could smoke weed every day. Smoke weed every day. So there's people like that. Right? And they're here because they want to go to school, they just want to be away from mom and dad. Most of those people are gone. Most of them. That's why I'm here. I'm so high right now. But, I'm kidding. I'm tripping on acid. But, It's going to be fun in a couple of years. This year, it's going to be legal. And then I can say that, and I'll go, yeah, we're all high too. It's going to make school really hard. It's going to come in and go, okay, guys. So, I have never smoked marijuana this week. Now, not this week. So, I don't know, but I think it's a good example. First year, a lot of first year courses look like that distribution. Some people really get it. Most people do it okay, and some people just, and there's a chunk of people, it's a good chunk of people don't get past first year, and you know that, right? And it's sad because they're your friends, and they usually are the guys that have all the weed. Things can also be leptokurtic, and I don't even know what these things mean. Don't worry about it. It's a way to describe things. Kurtosis is a way to describe how pointy a distribution is. How pointy a distribution is. So leptokurtic means peaked. That's this one. And platykurtic, the more pulled out it is, the more shaped like Paul Dupuis it is. Thank you. Thank you. I'll be here all week. It's great because he can't defend himself because he's at home on sabbatical. I know he made fun of me all last year when I was in sabbatical. Because he's a bad person. And he's not even a scientist. I'm kidding. I love saying things like that because he's a sociologist. But no, he's not. I'm kidding. Totally kidding. Also, really good scientist. The extras. It's recorded now. I can't edit it out. Don't let him know I said that because I have really no respect for him. He's like my best friend. Okay. Well, not really best friend. He's a good friend. We're acquaintances. But I don't know what this means. I know what they mean, but I would never ask you on a quiz what leptokurtic means because I don't know which one it is. No, I really don't. I know sometimes you get measures of kurtosis, so which you'll see sometimes in exploratory data analysis kind of outputs. You get things in SPSS. You can get things about distributions, and they'll give you measures of kurtosis, which I don't understand what they. Well, I can look them up. Okay. Skewness, sure. I think I could conceivably ask you something about it. I'm not going to ask you this because I just don't know. It's just another way to describe distribution. No, it's shape. So I thought I'd mention it. Distributions, of course, can be symmetrical or asymmetrical. So skewed distributions are not symmetrical, right? It can be unimodal or bimodal. A lot of times the stats distribution in 2126 is bimodal. Once you've got past that sort of skew thing, you get something that looks like this. And it's not that high. Very few people are doing poorly. Most people are getting B's and C's. And then there's a bunch of people going, this is like grade 4 math. Right? Remember that day in 2126 when it suddenly occurred to you how easy the arithmetic was? And you went, how did I ever make a mistake in this course? This happened to me. I was taking stats. I was in second year at Western. It was like one day I went, oh, I see. How did I ever, and I look back at old quizzes going, God, you're a moron. How did you get that wrong? Right? It was about a third of the way through the course. I was like, oh, I see. And that happens to most people. Some people it happens after they finish the course. But it does happen to most people, right? So yeah, unimodal, bimodal, the mode is just a number, right? Like the number, the most common number. It could be uniform. That's not pretty common in grades. You don't get as many D's as you get A pluses. That doesn't happen. What's a uniform? What's something that's distributed uniformly? You think of something? So every frequency is the same. You're as likely to get a 1 as a 2, as a 3, as a 4, as a 5, as a 6, and a dot. It's uniform. Here's a better example, because it's about hockey. And you're going to say, I don't know about hockey. I don't care. They're just numbers. They don't know where they come from. These really are numbers of goals he scored in his career, but you don't have to know about hockey to understand these numbers. There's Mario in the 2002 Olympics carrying their flag, and we finally won an Olympic gold medal in hockey for the first time since 1956. When was the last time we won a gold medal in hockey? It's pretty great. So there's his years. For those who don't know much about hockey, scoring 50 goals is a benchmark. That's something people don't tend to do. The most goals ever scored in a season is 93 by Wayne Gretzky. The fewest goals scored in a season is 0. It's by me. I never played in the NHL or really anything past PBB in Sudbury. But, okay. 53, 43, 40, 48, 54, 70. This is funny. This year they asked Mario, again, we can do this just by looking at these numbers, but that's a big jump. And also scoring 70 goals is a lot of goals. And you might, what happened? And there were two things. He played in the Canada Cup, remember the World Cup we just had? We used to call it the Canada Cup. Played in the line with Wayne Gretzky, so it showed him some things about playing, but also he quit smoking that year. Before that, he was smoking because it was the 80s and high-performance athletes sometimes smoked. 85, 45, what happened here? Well, he had back problems a lot, Mario. 44, that seems kind of low again. Oh yeah, that's the year he was off for 8 weeks with cancer. Yeah. Oh yeah, I got non-Hodgkin's lymphoma. I can't play. Oh, I'm back. I'm a superhuman athlete. If he didn't have all these problems, he would probably have broken many of Gretzky's records, actually. 69 is pretty, he gets hurt again, his back. 69, that's a lot. 50, still pretty good. 6, and then he retires. Retires for 3 years. Buys the team owes him so much money that he actually is given the team because they couldn't afford to pay him. So Mario Lemieux now owns the Pittsburgh Penguins. His number's been retired, he's in the Hall of Fame, and he decides he wants to come back and play again. He owns the team. So he comes back, he scores 28 goals, plays half the season, scores 28 goals. It's insane. I used to get a real kick out of it whenever he'd turn around and say something to the coach, because he could be like, put me on or you're fired. I mean, like, what's he going to do? And, captain, the C on your sweater, and the A for assistant captain. I always wanted him to have, owner. This is my team. And then he played on our Olympic team. That's 2002. And then he skipped the whole year because he was hurting him with his back. The final year he played was part of 2006, 2007. No, 5-6, and he played with Sidney Crosby when Crosby was 18. And it was like watching two magicians working together. It's an incredible thing to see. But he only didn't play very much. Anyway, I'm a really big Mario Lemieux fan, and also it's a nice set of numbers because it's got a lot of moves around a lot. Always get some hockey content in. That's the law. A histogram, I think, is a good start. But we're going to have to group these values somehow. We're going to have to group them somehow. So, what I did here, and again, the computers did this. I didn't do it. I put the numbers in and the computer just spat this out. You certainly can, and I'm just doing this for myself again. Remember, I'm doing it to understand the data. I'm not doing this to present to anybody. And you might say, what the hell's with that 90? What's that doing there? Well, that's because these are grouped, that's the midpoint of 85.5 to 95.5. The computer just did that. So those are the limits. The real limits are actually 85.5 to 95.5. Because those limits, these little dashes here, they have to be on half goals because you can't have half a goal and you don't want to have something in both things. This tells you something really right away. Mario had a lot of years under 10 goals, and between 5 and 5.5 and 10.5 or 15.5 goals. And that's because he got hurt a lot. He had health problems throughout his career. I'm convinced he literally could still play probably if he was not. if he wasn't hurt. Like he's the same age as me. I think he's like a couple months younger than I am. And if he didn't have those health problems, he probably could still play. I remember when they asked Jaromir Jagr, who's still playing too, he's like 46 now, who's the best player in the NHL right now. He was leading the league in scoring when he was about 35 years old, or 30 years old. And he said, "Oh, the NHL? No, it's hard to say. The best player in the world isn't playing right now. He's hurt. He owns our team. I'm sure he can still play." And he had some crazy years. Like those are ridiculous numbers. So the real limits, as I said, 85.5, 94.5. That tells us something. It tells us he had a lot of years. 50 is the benchmark, as I said. If you don't know much about hockey, 50 goals is the big thing. A lot of seasons like that. But we have to be careful about this, because it's going to make sure that scale made some sense. Now, in our case, the computer just spat it out, and it's fine. But sometimes your y-axis makes no sense. And usually people are doing that on purpose, to obfuscate things, to confuse you. So the y-axis especially. I'll give you an example in a sec. So here, one of the problems with the histogram is group data like this is you lose some of the richness in the data because we've grouped them. We don't know the individual numbers anymore. For a big data set, that's okay. This isn't that big a data set, but it's big enough. When I was living in Newfoundland and Labrador, in Cornwall, the most common way for people to heat their homes was oil. So heating oil. Okay? And the next most common way was people would have big propane cylinders beside their houses. It's funny, you have natural gas in Newfoundland. That's where a lot of natural gas comes from for the country, yet there's no natural gas infrastructure in Newfoundland. So you could have propane. People have wood. People have wood-burning stoves and furnaces. But the most common thing was oil. And the electrical company, of course, wanted to convert people to electricity. We all know how cheap electric heat is. It's like burning a pile of 20s in your house. So, we've got electric heat. The electric company sent out this mailer trying to get people to switch over to electric from oil. And, okay, fine. And they would give little incentives. They'd pay for a little bit of it to get you switched. It was, okay. And they say, it's not that much, that oil, at the time, oil was more expensive than electricity. Yeah. That's true. So the graph looked like this. So that was oil. And that was, see, it's a lightning bolt, electricity. The Newfoundland Lightning Power logo, or something like that. When you look at that, wow, it's twice as much for oil. So you look at the scale, and this was $100 a month, and this was $90. And then, oh yeah, $0. That's misleading as hell, right? So the scale, I think they obviously did it on purpose. They obviously did it on purpose. I almost called them on the phone, but I figured what use is that going to have? They're not going to listen to me. No one listens to me. Sad. You'll see this. Oh boy, it's great during election season. You see crap like this constantly. And this is what gives statistics a bad thing. There's lies, damn lies, and statistics. No, there's idiots, morons, and you. But the problem is that people that are running for office will use these expressions. They'll say things like, what's the unemployment rate? About 7% nationally? Maybe 8? Yeah, about 7. Let's say it's 7. It's probably right there. 7% unemployment. That's 7% too many, but whatever. So somebody will say it's 7%. That's pretty good. The economy's getting better. And someone else will say, do you know how many people are unemployed? And they're both saying the same thing. They're both saying the same thing. Yet, they're putting their own spin on it using numbers. And that's what they're doing here with the Yaxis. And it's really annoying when that kind of stuff shows up. That was the most blatant thing I'd ever seen. It was striking how annoying it was to me. And as you can probably guess, those of you who don't know me, I annoy really easily. It's a tough group. You go away for 1 year, you have 1 sabbatical, which I did so I wouldn't go insane, and now I don't know anybody. Well, I know like a couple of you. The rest of you still don't know what to make of me, and you're frightened of me or bemused. Oh, I don't care. I'm losing the will to live. So you can do a stem and leaf plot. Hey, look, stem and leaf plot. I think those numbers are right. I hope I copied them down right. If they aren't, I made a mistake. It doesn't matter. The point is, in fact, if you look at it sideways, it looks the same as that graph looked before. This is 0, 1, 2, so 17, 19, 28, 35, etc., etc., etc. Now, this is stuff they don't teach in elementary school, by the way. Did you know that? They teach stem and leaf plots in elementary school. Because a couple of years ago, well, more than a couple, but 4 years ago, my son, when he was in grade 7, was collecting data on what kind of chips people, I don't know what the hell it was, so they could make graphs and stuff. And it was other stuff too, would do his numeric, and he made a stem and leaf plot. I said, what are you doing? He said, I'm making a stem and leaf plot. Okay, carry on. And my son has autism, so sometimes things come out very, I am making a stem and leaf plot, Dad. Just not doing it. Well, that was weird. Most things that come out of John's mouth are a little bit off. It's not unlike his father. So you get a really nice feel for the numbers here. This is an ordered stem and leaf plot. I don't know, there is an unordered one. I don't know why you do it, but you could put the 6 here, the 1 here, and the 7 here. It doesn't matter. I don't know why anybody would do that. I think it's because maybe it's easier if you're doing it by hand. So you don't order it. You can interpret this like a histogram. As I said, you go sideways, you really pretty much have a histogram. It's easy to spot outliers, to spot outliers. I don't think there really are any outliers here. Because Mario Lemieux's career was a weird career. There were 2 Marios. There was Sick Mario and Well Mario. And Sick Mario's over here, where he looks like any other hockey player. And then he becomes a superhuman over here. I don't know what that is. And should spell check out have caught that. Like ought isn't a word. I can see SP for spelling mistake. That's still SP's not a word. I don't know. Preserves the data. Hey, we got the whole data set here again, so we got to copy it correctly. It's easy to get the middle or the 50th percentile. Aha. Which I've bolded so you can see that must be important. Also known as the median, which is 44. How do I know that? How many numbers are there? 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17. I want 8 on either side and 1 in the middle. 1, 2, 3, 4, 5, 6, 7, 8. Oh, look, it's 44. That was easy. It's very easy to. Notice we don't count 0 as one of the numbers, even though it's it's numeric, it's qualitative. Unless in a year we had 0 goals. I think the year where he got 6, he saved himself for the Olympics. It's incredible. Yep.
So when and if there are 16 in the scheme of the team.
Yeah, what we do at 16?
Yeah.
So let's say we didn't have the year we got 85. So we've got 8 and 8. So we go 1, 2, 3, 4, 5, 6, 7, 8. What's halfway between 43 and 44? 43 and a half. That's what you did. You just split the difference. Yep. Good question. Now, how often do you have to calculate this yourself? Never. There are literally online. Can you do it with the descriptives command in SPSS? Sure. You can also just online type in online box and or online stem and leaf plot, and it just says paste in your data here. Really, seriously. For most of these things, there's very quick things that work. You always have to be careful about them, make sure that they're the right thing, that they're not just somebody screwing with you. Doesn't happen that much. Okay, there was a bit of a screw up, so I'm going to try see if I can fix this. Okay. And that's all my fault, by the way. But we were at the part about stem and leaf plots, and that's when I lost part of the recording. So what I'm going to do is explain the rest of this stuff. And I'm sitting in my office afterwards. So you get the 5-number summary, which gives you the median, which is the median. That's the 50th percentile. Then there's the first quartile, and that's, in our case, it's going to be 18. And that's basically the middle of the first half. Okay? So you need halfway between 4 and 4, right? And then the other 4, the other 8, is going to be the third quartile. That's the 75th percentile. So now we have 5 numbers. We get the minimum, the maximum, the median, the first and third quartile. And the distance between the first and third quartile is also called the interquartile distance, which is a sort of a measure of spread. Okay? So like I said, we get 5 numbers, minimum, maximum, first quartile, third quartile, and the other one there. I'm such a loser. And the median. All right. Now you take these 5 numbers and you make what's called what's called a box and whisker plot, and that gives you an idea of the shape. So you've got, if you take a look, let's see, right here, we have the median. That's the middle there. You can see that's 44, and you got the maximum. That's the top of the whisker, and the bottom whisker goes down to 1. And then we got the third quartile and the first quartile. And you can see that this tells you a bit about about spread, because it shows there's just as much in that third quartile, as much data as there is in the first quartile. This just gives us an idea. It's a nice way to look at this, to look at these numbers. Okay, so it's just another way to visualize stuff. You never see this in a paper or something like that. We talked a bit about the central tendency before in class, before I screwed up my recording. That's basically one of the 3 properties necessary to describe a distribution. We can also talk about the shape, that kurtosis stuff and all of that I don't remember. And here's an example, okay? So here's 2 batches of numbers, 1, 5, 9, 20, 30, and 11, 12, 13, 14, 15. Both of these batches of numbers have exactly the same mean. It's 13. 1 and 5 is 6, and 9, 15. 35, 65 divided by 5. There's 5 there, so that's 13. And the same thing here. So we get 65, we sum them, and we divide by 13. By 5, I'm sorry, we get 13. But they're clearly different, aren't they? So as I say here, they're the same but different, these 2 batches of numbers. They have the same mean, and they're both symmetrical. That's great. So it's just as much on one side of the mean as the other. How are they different? And how indeed? Well, the one on the top is much more spread out. Okay? And that's pretty obvious. It's much more spread out. How could we measure how spread out 2 things are? Well, how would we measure spread outedness? Well, the range is an idea. You could certainly use that. And here we got 1 to 30 or 29. Sometimes people do that. Or 11 to 15 or 4 in this case. You can do that. That's also fine. It's not going to be super helpful to have that. It's a start. It's exceedingly crude, though, right? Like it's a very crude measure. We can also use the interquartile distances, which I'm not going to calculate, but that's, remember, third quartile minus first quartile. Again, that's pretty crude. We need something better. We need really something like we can calculate, something like a mean. So sort of like the average amount of that the data are spread out. That'd be good. Let's do that then. Right? So what we've done, I've got the mean, and this is the first batch of numbers, right? 1, 5, 9, 20, and 30. And we go what? 1 minus 13, so negative 12, plus negative 8, plus negative 4, plus 7, plus 17, divided by 5 is 0. Well, that's not going to be very much use to us at all now, is it? Damn. In fact, it's got to sum to 0. When you think about what the mean is, it's like a balancing point. So you're going to have as much on one side as the other. It has to. If it doesn't sum to 0, you made a mistake. How do we get rid of negatives? Absolute value. So we get a quantity called the mean absolute deviation, which is just taking the absolute value, which is when you put those bars on the side of things. And that gives you a value here, and we get a value of 9.6, and that seems all very reasonable and useful. At least it's a number. But it's actually not nearly as cool as you might think. For our purposes, in fact, the mean absolute deviation is actually just a dead end. It's useful in non-parametric statistics, but it's not useful in parametric stats, which is the kind of stuff we're going to do. Which is too bad, because it's intuitively exceedingly pleasing. So I'll continue recording this next time in class. Thanks for bearing with me. Sorry about the screw up.
Has to be a better way to do this. And obviously there is, the class would end right now. And we just stop. You go, well, that's it, we're screwed. So how else can we get rid of those nasty negatives? The nasty negatives. Is this mic on? I think I'm recording through the wrong device. Just a second. This just in, YouTube viewers, I was using this mic. So, how do we get rid of the negatives? We can square the deviations. These deviations, x minus x bar. The other way to get rid of negatives with values is you square them. Right? So, negative 9 squared is 81. It's not negative 81, it's 81. We're going to multiply a negative times a negative e to the 5. Cool, so let's square them. Let us square the numbers. And on that day it was said, let us square the numbers. So that's what I did here. Okay. Negative 12 squared, 144. Negative 8 squared, 64. Negative 4 squared, 16. Positive 7 squared, 49. 17 squared, 289. Add them all up. Divide by 5, because n was 5. We get 112.4. Well, that's a number. So that's a number. That's good. We got something. So we're getting closer to where we want to be. Questions so far? All right. It seems big, though, doesn't it? Remember that mean absolute deviation? We had like 12 or something for this? It should be similar to that, and that's way bigger. It's like an order of magnitude bigger. It's squared units, not the original units. It'd be like saying, it'd be like measuring height in square centimeters. It doesn't make any sense. So let's see. What's the opposite of squaring something? It's the square root. So we take the square root of 112.4. So you hit the square root button on your calculator, and that's easy to use. It's just a button. And you get 10.6. And you should, every step of the way using a calculator, you should be double checking just in your mind, does this arithmetic make sense? You really should, because you might have just hit the wrong button or put numbering too many zeros like I was talking about the other day. So just remember that when you hit this number, you get this number, 10.6, you say it was 12, was it 12 point? No, 10, what was the number again? 112 point something. Well, 112, the number has to be somewhere between 10 and 11. Because 10 squared is 100 and 11 squared is 121. Yeah. So, if that's the case, it's got to be somewhere between those. Just keep that in mind. I know it's not easy when it gets really big, right? What's that horrible? That sound, if you took my memory class, you're in that class, it follows me. There's a horrible, high-pitched whine that is not coming from my gear. It's coming from somewhere else. Is it coming from there? I don't think so. But now I can't resist getting on a chair and listen. It is. Piece of crap. Okay, so I'm going to turn something off. Why? Who is what with the volume and the thing and the stuff? What is going on? Okay. Oh. You know what I did? I turned down the volume. You know what the thing is? People use stuff and don't leave it in a known state. Those people are bad. They're worse than like Al Qaeda. Okay. So no, they're not that bad. They're not that bad. That was a horrible thing to say. Okay. So 10.6, that's a reasonable number. There is a problem, and I know that you guys know this, but there is an issue here. The formula I've shown you has n at the bottom as the denominator. I still have to go numerator, denominator. And I know that just makes sense, that it should be the number of numbers. I know it makes sense that it should. However, who said this was supposed to make any sense? Well, actually, hopefully I can convince you what the deal is. It's in fact supposed to be n minus 1. It's supposed to be n minus 1. So, we want something that's going to be an unbiased estimator of a parameter. That parameter in this case is called variance, or standard deviation. The same quantity in the population, a parameter. If we use n, we get what's called a biased estimate. It's a little bit too small, but we know by how much. The cool thing is, we actually know by how much. Now let's see, the screen's everything's out of whack. I don't know. The population parameters, variance and standard deviation, have big N, or the total population on the bottom. That's their numerator. Sorry, denominator. The sample statistics used to estimate those parameters have n minus 1. So population parameter, the two p's go together, sample statistic, the two s's go together. A statistic described as a number that you calculate that describes a sample. Okay? A parameter is a number that describes a population that you actually typically can't calculate because you don't have all the data. You don't usually have the whole population. Right? You theoretically could, but you usually can't. Practically, you can't. It is typically an unknown number. That's why we try to estimate it. Population parameter, sample statistics. Parameters describe populations. Statistics describe samples. Population is all the cases of interest. It's a very simple, straightforward definition. All the cases of interest. In statistics, you would say in other courses the number of people in a country, but that doesn't really describe a different thing. And a sample is a subset of the population. A lot of people seem to get really caught up in the idea that, well, let me back up. There is a population of, let's pick a population of people. That's a Peter Piper picked a population of people. So what's a population? Think of one, just anything. Think of one. Somebody, okay, fine, I'll do it. I'll go university students. Good. Is what we have in here a sample? Yeah, of course it is. It's a subset of the population. Is it representative? No. No, we have, including your instructor, 3 men in the room. 3. I think it's 3. Wow. The sex ratio in the school is not 22 to 3. It's about 45, 65, I think, which is typical in the university sector, which is too bad because more men should go to university, but that's a whole different discussion we can have. If any university can figure out how to get men to go to their school, then any enrollment problems disappear. Because suddenly all these guys are going to school. Don't go to school. I don't know why that is.
First person to figure that out will win all kinds of stuff. I'm serious. Alas, that is a different thing. So we're not a representative sample, are we? Also, I said all Algoma University students, so I can't be included there. I'm not a subset of that population. The Algoma University community, okay, then we are. What kind of words people use? Oh, we're a learning community. No, we're a university. I have certain views on things that really don't matter towards this course, but I like to spread them anyway. So, it's not a community. It's not a... We all get around and we join hands and say, no, I have a job, you have a job. It's a job. Yeah, so we're much more skewed towards women in here. Hard to say. I think we're a little whiter than the population, of students here. We certainly have more expertise in psychology than the average student here. However, that doesn't mean you're not a sample. A sample can be a non-representative sample. It's still a sample. You gotta keep that in mind. So people get really worked up about representativeness, and that's fine. They should in certain cases. But if someone said to you, what is a sample? If someone said to you, what is a sample on perhaps a quiz type situation, you would just say a subset of the population. You have to say a representative one, because you don't have to be representative. Okay? And for some things in, say, psychology, which I think you guys are mostly interested in, it doesn't matter to be representative. What? For basic cognitive processes, it doesn't matter about your X and Y chromosomes and your gender identity, and it also doesn't matter about your ethnicity and the language you speak and the religion you have or the religion you don't have. Or the language you speak, I mentioned that, color of your skin. All our memories work the same. Our perceptual systems work the same. So it's not like, if you're doing memory work, you often hear this. People go, I want a representative sample. Why? You want to really represent, generalize humans. You're all human enough to be subjects of an experiment. If I want to say how Algoma University students think, I better get a representative sample. Like, how they think about an issue is what I mean. They're not how they actually think. It's how they think works the same as how somebody thinks in, I don't know, let's pick a country, South Sudan. I assume no one here is from South Sudan. Is that weird? And surprising. So samples, populations. The thing is, we're trying to estimate populations. They're more interesting, right? We would underestimate the population parameters if we had n. This is nice. Like we know, in fact, by how much. There's really cool proof of this. There's really cool math behind this that I'm not going to show you. And it's partially because I can't remember it. But it's partially because I don't think it would help you anyway. It's of no real use. So these are the sample statistics, S squared and S. It's easy to calculate, and it makes you look smart if you can write down a formula like that, because people that don't know any arithmetic and math at all think you're really brilliant. Oh, you can use Greek letters? Oh, you must be smart. So capital Greek letter sigma gives us sum, so we sum them up. And then you have a square root right here. That's great. This, by the way, if you calculated this and you get a negative number, what does that tell you? You did it wrong. Because you can't get square a bunch of stuff and get negative numbers. Well, you can, but it has to be using I, an imaginary number, which is the square root of negative 1. They still teach that in school? But I go to some kind of weird special school. I don't know. Okay. So you know this, right? So actually, when we do the calculation, it's this. So now I just did put n minus 1 on the bottom. So we actually get 11.85. Square root of 140.5. and you think to yourself, square root of 140, 144 is going to be 12, it's going to be close to 12. Oh, good, it is. You got getting a feel for what happens with numbers when you play with them a little bit is a really important skill in life generally. You know, it's seriously, when you get a bill somewhere and it tells you how much it was and it tells you how much the tax is, you should be able to look at that and go, yeah, that makes sense. You shouldn't be able to just go, oh, what kind of magic is this? Did you ever go into a store during a power failure and they can't make change? I went into a Max once. There was a power failure in our neighborhood. I went down to Max and thought, well, I don't know. I guess I'll go buy some what was I buying? Coke, and I'll just sit here and I'll mix it with rum and get hammered because there's nothing else to do. Because the power's out. This was a few years ago, before I had a special fridge dedicated to nothing but pop for drinking. So I'm going down to the store, and I said, I'm sorry, I can't make change. I said, what do you mean? Can you not open the till? He said, oh, I can open it. I can't do the... I said, it's the Coke, the big 2-liter Coke. I said, it's $2, it's $1.99. It's $2. I looked at him, I said, what's 13% of $2? He looks at me, I said, it's 26 cents. And this guy behind me, who's also trying to convince him to open up the till, pulls out his phone and goes, he's right. I said, guys, it's 13 times 2. It's not that hard. I am not a wizard of any sort. The white hair, maybe, but I'm not a wizard. So just getting a feel for numbers is an important, seriously, it's an important life skill. But it's really important in this kind of thing because we tend to trust computers way too much when they do calculations or calculators. So being able to look at something and go, yeah, that's fine. That's a good thing to be able to do. I used to ship things out on eBay when I lived in Newfoundland, sell things on eBay. And I'd ship them out and I'd package them myself and I'd take them to the post office, and it's we're living in a little town outside of a little town. So the guy in the post office knew me, and he even gave me a bunch of customs forms, and I would walk up and I'd say, it's going to be $3.85. He goes, how do you always know that? I said, I have a scale, and I looked it up and I can add. It's really not complicated. Yeah, you also get to look like you're magic if you know how to do arithmetic. It's just incredible to me. Okay, for the population, we use Greek lowercase letters, Greek small letters, sigma squared and sigma. I know it's confusing because it's also a sigma, has a capital sigma. Notice how, these are actually Greek letters too, by the way. It's a chi, but let's say x. X minus mu squared. Mu is the population parameter for mean. And x minus mu squared, the square root of the whole quantity divided by n. Okay? All right. Questions so far? This is all stuff you ran into, I know, but even if you don't feel bad if you have questions, that's what I'm here for. Please.
So when we're doing all these, this is all just coming back to how to measure the spread.
That's all it is.
Right? The
All it
variance,
is.
the standard deviation.
That's all we're doing. Yep. How are the variance and standard deviation affected by extreme scores? There's our two batches of numbers again, 159, 2035, the standard deviation is to 30, sorry, standard deviation is 11.85. Okay, or one batch of numbers. Let's put on a no number. How about 729? Why did I pick that? I don't know, but I did. I think it's 727 squared, actually. I don't know why I picked that, but I did. So 159, 2030, 729. We've now thrown in an extra number. And now our new mean is 132, so the mean's affected by the adding a new extreme score. So then is the standard deviation. Our new variance is 85,555. 0.067, and our standard deviation is 292.5. The mean's affected by the extreme score, first with the ellipse, and therefore so is the standard deviation. Look at how you calculate the standard deviation, right? Remember, it's the sum of x minus x bar squared
over, let's not worry about standard deviation, let's just think about variance. Because they're the same, one's just the square of the other. Mean's in there. The bigger number this thing is here, the bigger number you have in your on the top of your fraction. Right. The bigger number you have in your numerator, the bigger the fraction. Just the way the world works. All right. Questions? Good so far? You still okay? Yeah, please.
How do you get the variance?
How did I get the variance there? Oh, I just added up. Well, I figured out what the mean was, which is 132.33, and I did 1 minus this squared plus 5 minus this squared, 20 minus this squared, 30 minus this squared, this minus this squared. Added all those up and divided by, in this case now 5, not 4. That's all it is. How did I do it? There's a button on my calculator. But yeah, it's the same formula, except we've added one more number, so then we divide by 5, and we've also got a new mean, so we had to put a new number in there for them. That's all it is. Nothing too fancy. How can we use this to our advantage? Well, there's a quantity called coefficient of variation, which is interesting because here's actually a piece of data. This is looking at people studying for a test or not studying for a test, and I believe the questions are physics questions, if I'm not mistaken when I think back to this. I think it's physics questions. Doesn't matter what it is. But they're multiple choice questions. Two groups, a study group and a no study group. The study group gets 69.6. And a standard deviation of 10.6. The no study group gets 46.6 and a standard deviation of 6.8. Okay. And those are actually real data for this cat. In fact, I believe this is mentioned in the book. I think that's where I got this example. You could look at this and make a very strange conclusion that would be supported by the data, by the way. There's more variation when one studies than when one does not study. Doesn't that seem weird? It's exceedingly counterintuitive, right? Isn't it? You would think there'd be less variation when one studies because you're going to more likely to know the right answer. So shouldn't there be less variation? Except that this shows that maybe there's more variation when you study. That's weird. In fact, that's completely counterintuitive and probably against everything you've ever experienced in your life, but also probably against years and years of stuff in cognitive psychology. Well, we have something called the coefficient of variation, the CV. And what you do there is you take the standard deviation and divide by the mean. And when you do that, because the standard deviation is a function of the mean. The bigger the mean, the bigger the standard deviation. Right? Because, again, looking back at the formula, right? So the bigger the mean, the bigger the standard deviation. Why don't we standardize it? And now they're almost the same number. That actually tells us that this difference is simply due to the fact that the mean is bigger in the study group. That's the only reason it happened. It's got nothing to do with the actual variation itself. It's got to do with the fact that you're calculating a quantity and it's dependent on this value here. Okay, it's dependent on that value. Questions so far? You might think to yourself, why is it that we're dividing by n minus 1? Dave gave me an explanation, which I find somewhat displeasing, which is, well, it doesn't work if you do it by n. You get a biased estimate. Well, go into a little more detail. When you calculate variance, you're calculating variance based on a set of numbers, right? Okay. How many numbers are there? Generally, there are n numbers. Okay? Those numbers are free to move around as they wish. I know that's a very strange thing to think of. But the numbers are free to move around any way they want to. Yes, numbers don't want things, I know. But they're not completely free, are they? They can move around. In fact, I can tell you about some numbers. I could say the mean is 10, and there are 5 of them. I can even tell you, and I'm not going to because I don't feel like doing that arithmetic in my head right now, what the standard deviation would be. But let's just start here. These numbers can move around. Right? So, I don't know, let's pick, give me some numbers. Tell me a number. 25, there's our first number. What's our, give me a second number. 2's a good one. That's number wang. You ever seen Mitchell and Webb? Nobody? Look that up. Look up number wang, Mitchell and Webb on YouTube, and it's very funny. Okay, or you'll find it really weird, you won't get it at all, but I don't care. I think it's funny, and I'm the prof. Another number. Give me another number.
7.
7's a great one. I love 7. Here, one more. Give me another, please. 8 is also a good number. We got to get a mean of 10. Oh, now we can't just pick any number. Let's see, 27, 30, 27 and 15. That's 42, right? 42. So it's got to be 8, doesn't it? Yeah, it's got to be 8. Because that had to add up to 50. It had no choice. There was no freedom left. It had suddenly become a repressive authoritarian regime of numbers. There was no freedom. A repressive authoritarian regime of numbers. It's the worst. That's the title of my autobiography. Wow. That's weird. You know, you could do that a bazillion times. You always have, the final one's always fixed. The final one's always going to be fixed. So when we say we know a mean, which we have to know to calculate standard deviation, we divide by how much the numbers can vary. It's called the degrees of freedom. It's the number of items you can assign arbitrarily. You have lost a degree of freedom. Which leads to the only vaguely funny statistics joke. And I say vaguely funny because it really isn't funny. These two unbiased estimators are talking in a bar. It's already weird. And one looks at the other and says, what do you think of married life? And he says, it's okay as long as you don't mind losing a degree of freedom. So, that's a statistics joke. It isn't funny. So one wonders if it's actually a joke. Though you all laughed, mostly sympathy laughs, I appreciate that. It's not my joke. It's told to me originally in graduate school by our stats prof, Dr. Spence, who influenced my view on statistics a lot, and he was from Scotland. The numbers don't know where they come from, Brodbeck. So he'd say to me, they don't know where they come from. You can do anything you want to them, and eventually they'll tell you what you want. He found out one day I did an impression of him. It was before we were studying. for our final, which is a 4-hour final, open book, you know. And I was in grad school, and I'm up in front of the class doing an impression of him before he comes in to give us our final exam. He gives us our final exam and he leaves because it's open book. He comes back. Back then I had very long hair. It was in ponytail. And he comes back in and he's gone to a custodian's closet and he's got a broom with like a white one, and he's put it over his head. And he's somehow found a long overcoat, because I used to wear it's 1988. I used to wear a long black overcoat and motorcycle boots with chains on them and a beret. I was very stylish. He comes in and he comes in like that and he goes, "Hey dudes, I can't see anything." He was so cool, and I'll never forget him. So now and then you might even hear me, the little Scottish brogue, when I talk about this stuff, because I can't help but think of Ian Spence when I think of statistics. He's really a great teacher. And he was hilarious. He also used to say, "Undergraduates, they're stupid." Like, he just didn't say that. Yep.
Sorry, just to move on, before we move on from the slide, can you repeat what CVS stands for?
CVs. Coefficient of variation.
Okay.
I should maybe, I actually have to put a apostrophe, not really. Yeah, coefficient of variation, sorry. Yeah, Ian was great. He was a great teacher. This is really bugging me how that's named. Anyway. So you've lost a degree of freedom. Whenever you've estimated something, when you look at this quantity, when you calculate it, you say to yourself, I have to have estimated something. I have fixed a value. It's this. Every time you look at a formula, see how many things are in there that you already had to calculate first. In this case, there's one of them. It's X bar. That means you've lost the degree of freedom. You start out with n degrees of freedom, but you lose one as soon as you estimate something. If we had a formula of estimating 2 quantities, which we will, you lose 2 degrees of freedom. Okay? Other questions? So the coefficients of variation. This again is not something you see in a paper. This is something you see when you do your own statistical, when you do your own sort of exploratory data analysis. It's for yourself. All right. A few key points. We want to learn about populations, not about samples. We learn about populations by studying samples, but no one really cares a great deal at the end of the day about your sample if it's done properly and you're using it properly. We estimate population parameters with sample statistics. We want unbiased estimators of parameters, and that's why we have to take into account things like degrees of freedom. The very neat thing about this stuff is when you do an estimate of something, there's math behind that telling you why it's biased in one way or not and how it is. And if you're in graduate school and poor you have to actually do that, and we didn't. Ian thought it was ridiculous for us to do proofs, so we didn't do proofs. He showed them to us and said, if this means anything to you, that's great. I don't care if you understand it. I want you to have an intuitive feel for it. And he's right. I feel exactly the same way. So if there's somebody in here that's kind of a math nerd and really wants to see the proof, we can go to my office afterwards and I can pull out Experimental Design by Kirk, which is a great book, and you'll end up using it in graduate school, and I can find the page with the proof on it. Or you can just believe me, pretend you're Catholic and I'm Pope Dave the First. You've been watching that new show, The Young Pope, with Jude Law as the Pope on HBO? Still not sure what to think of it. It's pretty weird.
Is Jude Law really young?
Well, he's for a pope. Yeah, for a pope. 42 is young for a pope, or 52, whatever he's supposed to be.
Middle-aged pope was better.
Middle-aged pope is a really shitty title, though, right? Yeah.
I like it.
Yeah. There's the old pope. We already had that show. We've seen it quite a few times. It's a weird. I'm still not sure how much of it's a dream and how much it's reality. The opening sequence where he climbs out of a pile of babies, and I'm not making that up. It's just weird. And when it's weird for HBO, that's saying something.
I read a bunch of tweets about that show.
What's that?
I read a bunch of tweets about that show.
Yeah. I read a
How
really...
it's like just weird.
It's just odd. You know how sometimes you watch things on TV and everybody likes it and you go, it's not good, it's just weird. Everybody says it's good because they don't want to people think that they misunderstand it. My view. That's for our review of TV shows for today. Young Pope. Catch it. Catch Young Pope fever. Oh, that was funny. I know you don't find it funny at all, but this is one of these things. I sometimes say things in class just so I can tell friends of mine I said them. And that was one of them. All right. I got to throw this in somewhere, so we're going to throw it in here on the last slide. Sometimes you can take a distribution, take a variable that is distributed some way, and we're going to call that variable in this case x, and you can do things to it. Okay. What is the E means expected value, var means variance. What is the expected value of, well, it shows you right here, but let's think about this. The variable x. What's the expected value of the variable x? Well, that's the mean. The most, we would expect to get the average, wouldn't we? The long-term running average, the expected value, we would expect to get the average. If I gave you a 4-choice multiple choice test, in a language you can't speak, in an alphabet you don't understand. Let's do that. Perfect. How many do you expect to get right? Well, 25%. Some of you are going to get really lucky and get like a 60. Unlikely, but some of you will. Some of you are going to get really unlucky, get none right. But on average, you expect to get 25%. If I add k, a constant, to a variable, well, now I expect x bar plus k. So again, think about this. Think about now a class. Let's pretend that I'm teaching intro psych, which doesn't happen very often. Let's pretend I did it. And let's pretend on the first test the average was 45%. That wouldn't be enough. I would be concerned. I would have students ask me to curve the things, and they don't even know what that means. But let's pretend they do. Well, they actually don't, because they just want me to add a constant to all the scores. If I want to make it 45%, and I want to make the average 60, what do I add to each score? Average is 45, I want the average to be 60. What do I add to each score? 15, right? So if I just add 15 to every score, the average goes from 45 to 60. So the expected value of x plus k is x bar plus k. All I've done is I've taken the distribution scores, and I moved it over. What's the variance? What happens to variance? Well, as you can see here, nothing. Because I haven't changed the shape of the distribution, I've just moved it. I've just picked it up and put it somewhere else by adding a constant. So it's not going to change the shape. It's not going to change the spread outness, is it? I'm just going to move it all over. What's the expected value of x times k? Why would you do that? This is how I actually do things to tests. If I do, but it's very rare when I do it, and it usually happens in something like intro. And I don't teach intro very often. I haven't taught it in a regular term since 2009. I've been told I'm a little intense. I like teaching intro, it's just that I also don't like it. I like teaching things to people and they know literally nothing. It's kind of great when people, because you don't know psychology when you come in, right? Or you think you do, you think it's Freud, and then you find out on day one that that's all bullshit, and then you go, oh, really? And it's all new. That's kind of exciting. The downside is you're teaching people in first year. So we have other people who are better at that than me, so they do that, and I get to play with numbers. I actually like it, but like I said, I don't think I'm nearly as effective at it as I once was. Anyway, that was true confession time. When I want to move an average up, I don't like just adding a constant. Because what that does is it rewards people who did poorly more than it rewards people who did well, percentage-wise. If I add 10 to everybody's score, and you got 5 out of 100, I just tripled your score. And if you got 90 out of 10, I've added 11%. That's not fair to me. I instead like to multiply times a number. So I multiply all the scores times some number. It gives me the same average, but people on the high end, their marks go further up. Encourage people. Typically, again, I've only ever had to do this in intro. It doesn't happen at any other level. Okay. If we multiply all the scores times a constant, the expected value is going to be the x bar, the mean, times the constant. So if the average is 45 and I want to get to 60, I find out what times 45 equals 60, and I multiply all those numbers times that, and it gives me the right mean. Okay. That would be 12, 9. I multiply times 4/3 in that case, because that'll move 45 up to 60. Okay. We're multiplying, we're changing the mean, and we're multiplying it. We're not just moving the whole thing over. We're moving it over, and we're getting one end bigger than the other. Because the higher scores get way bigger than the lower scores do. They get a bit bigger. I can't stand like this forever. Do you get the point? So, that's going to change how spread out the numbers are. In that case, the variance, and remember, variance is a squared quantity, so the variance of x times k is s squared sub x times k squared. So s squared sub x times k squared. So if we want to multiply all the scores times, I don't know. Let's say our constant's going to be 5. Let's make it easy. So let's say our mean, in this case, let's say our mean is 10, and our standard deviation is 5. Let me just make the math easy. Okay, and k, our constant, we're going to multiply all the scores times 2. Let's do that. So, if the expected value of x times k is going to be what? In this case, so x is 10, k is 2. Yep. What's the variance of x times k? Standard deviation is 5, so the variance is 25. We're going to get 25, yes, times 4 is 2 squared equals 100. Exactly. So it spreads it out. It doesn't just move it, it also spreads it out. Why am I bringing this up? Well, actually, you sometimes do this to, I had to throw it in somewhere, and sometimes you actually do this to numbers. There are occasions when, and we'll talk about this a few days after the first test, there are times when you do things like this to your numbers. You don't usually multiply times a simple constant, but you do something like that. Or you don't just, sometimes you do add a simple constant. And there are very good, sound reasons to do this. This isn't cheating in any way or something weird like that. Yeah, 5 times 5 is 25. 2 times 2 is 4. 25 times 4 is 100. Can't see, but I can hear pretty well. So the standard deviation, by the way, is just going to be S times K. Just like K. Yeah, S times K. So 5 times 2 is going to be 10. And you say 5 times 2 is 10. You double check your work. 10 squared is 100. Excellent. I did it right. Does that make sense? I'm hoping these make sense. And the reason we do this sometimes is because the variable, the distribution, isn't the right shape. And sometimes that happens. And we make certain assumptions about the statistical to do certain statistical tests. And sometimes the variable has to be a certain shape or something to that effect. And it isn't, but we can fix it. Okay. You might think that doesn't sound fair. Well, we can measure your height in 2 different things, centimeters and inches and feet. We do that all the time. And they're just transformations of each other. Number of inches tall times 2.54 is number of centimeters. That's all they are. That's all it is. Right? Fair thing. You hear it on the radio whenever you hear radio stations here, because we live on the border, and you hear that the temperature is -2 Celsius, or would that be in Fahrenheit? About 28 Fahrenheit. Right, so it's -2 Celsius or 28 Yankee imperialist running dog lackeys of the capitalist landowning class degrees. little North Korean there for you. And they're both perfectly valid. There's nothing wrong with Fahrenheit, actually. It's different. It's 5, you multiply it times 9/5 and subtract 32. Or add 32, sorry. Wow. That's a crazy transformation. It's still just a transformation. You've actually done a multiplication and added a constant. Does it make it any warmer over there when it's 28 and it's -2? No, it's the same thing. Just measured with 2 different scales. Okay? Or when you convert your money. Right? Which you do all the time. You go over to St. Marie, Michigan to buy something, and you have to look and go, is that actually worth it? And you actually have to do this. You have to multiply times a constant. And you actually have to add a constant, because you have to add on how much it costs you to cross the bridge. We do it all the time. It's still money you spend. Right? So there's nothing magical about doing these things. You actually do them all the time. You just don't think of them as variables and distributions is all. All right, questions? We have a quiz on Thursday. And I think I'll stop there because I don't want to start the new bit, because why should I?